why it is helpful to be part of the ROS community there is because we can see how other people are incorporating SLAM into their context and use that almost as, imagine that maybe you don't have to imagine, but you're a team of roboticists that are pushing cutting edge applications in whatever context, but you yourself are not like doing a PhD on anything in particular. And so you're going to have an easier time if you can access a community of people who have this ethos of like, how can we lift each other up?
Thank everyone for joining. Thank you, Deanna, for being here. We're excited to continue the Spotlighting Women in Robotics initiative here at Ekumen. We're joined by a person, a professional that whose work sits right at the intersection of cutting-edge technology and life-changing robotics. Deanna Hood has worked in really interesting, innovative, and impactful projects, from working at Open Robotics, developing ROS2 code for some applications, like some of them used by NASA, to creating a robot that helps children learn how to write. And lately, Deanna has been working in the medical field, building a skin printing robot that helps burn survivors. And then also she's currently working at Vexev, building an imaging robot that helps prevent and treat diseases. Deanna is also an active member of the ROS community. Some of you may have seen her at the ROSCon talk, where she explained how she used ROS tools in her latest work. And yeah, we're excited to have you here. It's a pleasure, Deanna. So before we dive on the technical part of your work, do you want to say a few words about yourself?
I think my branding must be on point on the internet, because I feel like you described me how I would describe myself. I'm a roboticist. I've intentionally designed my career for social impact. And sometimes that means making financial sacrifices. Obviously, working on ROS2 at Open Source Robotics Foundation is a nonprofit. And since then, like working in research or in startups, you know, there are trade-offs that come with that, but for me, it's worth it to know that the robots that I'm working on are actually helping improve people's lives, provided that we can ship successful products. So turns out that's easier said than done, but it's something that I really enjoy being a part of, cutting-edge stuff, like you said.
That's amazing. Maybe later we can discuss like what it takes to get a robot to like the production stage. But first I wanted to ask you, what led you into working in the robotics field, and mainly bioengineering?
On like a technical note, I got into robotics through a master's of robotics, but that was only after studying electrical engineering, and they snuck in some coursework on like localization mapping, and I realized it was full of maths. And even doing an electrical engineering degree was only because I'm a mega maths nerd. I started university at 15. I just wanted to do a maths degree, but because I was so young, I figured I would do something else more like practical as well. And so that's how I became an engineer turned robotics engineer. On the bio side, I think it snuck up kind of in parallel. The older I got, the more I sort of had this awakening of like, oh, but I also want to have a connection to impact. And so it didn't, I worked in electronics and like power industry for a few years, and that in that space, I also was working on like tech for either in development, so like diagnosing pneumonia in children in Mozambique was one of my like electronics focused projects, or a brain controlled car simulator for people living with paralysis. That was like not robotics, but really like that was my electrical engineering thesis. And it came at just the right time because I was getting kind of jealous of my friends who were studying medical engineering, that they were working on like the cool projects and I was just working on electronics. But then I realized that it's a layer that comes on top. Like the reason why you're doing your work is it's a different layer to what you do every day. And I love what I do every day as a roboticist. So then I just need to add that layer on top of like why I do it. And since then, like you said, I've gone into educational robots. Like ROS is used in everything, including environmental applications like monitoring penguins in Antarctica and in space, and now working in medical devices. But always, I have to really triple, quadruple remind people of this. I'm always doing it as a roboticist. I'm not the medical engineer. Someone has to be, but it's not my personal interest. I want to be like just writing, planning algorithms or something.
Yeah. I think so, but you do have to work with all these medical engineers and medical specialists that can help you with this work, right?
Yeah, and that was a big transition from so working on the ROS team. Imagine when I was starting, I was on the ROS team when we were writing the ROS 2 like rewrite of ROS 1, and I was there during the alpha and beta releases, so writing really early features. So if you've ever done any logging functionality in ROS 2 in any of the languages, it's based on like the framework that I bootstrapped. And that was all just done with like a team of 5 people. And maybe by the time I was there for a few years, and maybe by the time I left, it was more like 10 people. But however many it was, we were all roboticists. And so we could tell each other what we were working on sort of in our native tongue. And we didn't have to translate it into why someone should care about what we're working on. We all just implicitly understood, okay, you're adding the throttling functionality to logging. We get it. Whereas since then, I've worked in really multidisciplinary teams, and the skin printing work that I did at Inventia, I was the only roboticist in a company that by the time I left was like 90 people, the only roboticist. So in order to have a conversation about my work, I either had to translate it into like impact that people can engage with, why I'm writing different features, or kind of speak with roboticists from outside of the company. And I was working with KUKA at the time, so like I made close connections with them so that I could have people that understood inverse kinematics, for example, singularities, like, okay, we can speak our native tongue. But that's the trade-off of like being in a robotics company versus being in a multidisciplinary team, is that the skills you have to develop or the communication that let you translate between what you're doing and why you're doing it.
Yeah, I think that happens in a lot of projects because robotics nowadays is everywhere, let's say, and luckily I would say. So I think that skill is critical for all of us. So before we move forward to more specialized medical robotics, I want to ask you, what was like a technical challenge that you remember at Open Robotics?
In a way, we knew too much because we had already seen everything that ROS 1 could be used for. And so I remember that it was challenging to design for everything from scratch, but it was an intentional challenge that we took on. So the logging functionality that I wrote intentionally was written in C because we intended for it to be the same behavior when it was wrapped by client libraries in Python, C++, Java, whatever everyone has gone on to add. So that was like, if you were just writing a Python client library, you would just start with the Python logging functionality that's already there. But because we had this vision of like, let's do cross-platform from the beginning, or like cross-language, but also like Windows support from the beginning, the development experience is slower, but intentionally, so that then you don't have to redo it when you go to add new client libraries. And like I said, so that they have the same behavior, because if there are some nuances in ROS 1 where different client libraries behave differently, and it's because they were written completely independently, the different client library stacks. Now, maybe they still behave differently, but it means that if you wanted to add like a random esoteric language wrapper, you don't have to do all of the core functionality that exists in the common client library and C. You just have to wrap that and expose it in whatever language you're interested in. And it pays off, because then you see people really contributing, like, okay, here's the Rust client library, here's the JavaScript client library, whatever.
Yeah, so kind of it made sense to make, this is something that at least I don't see so often in robotics, where you said that it made sense to spend more time developing it for everyone to use it, rather than make it quick so it is available for everyone. Yeah.
I feel like another example I have of when that has worked well is, like, I think it especially makes sense when you're trying to make a framework or an API, and you want to give people not just the flexibility to build on top of it, but like the creativity. So before I worked on the ROS team, I was using the Aldebaran Now, a small humanoid that they didn't really intend to. It was designed for like low-key HRI, kind of with children, and that was the context that I was using, and it was for handwriting, that children could teach this robot how to handwrite. And one of the downsides was that it itself couldn't write very well, because that just wasn't what it was designed for. And I was working in a lab where Séverin Lemagnon had set it up to be using ROS, and as a result, I could easily connect a tablet to this humanoid and have it pretend to write by just being synchronized with letters that appeared on the tablet. And ROS made all of that like prototype we were in schools within 3 months, because like we just had to add this layer on top of synchronizing those devices and have the idea to do it in the first place, and not get stuck trying to make this relatively inexpensive robot actually write with a pen. So I mention it because I have one of my former colleagues on the ROS team used to work at Aldebaran, and he said that the video of the Now doing that work with children in the handwriting context kind of like, I don't think it went viral inside their company, but it was certainly widely shared, because they didn't expect people to use the API in that context. And I feel like that's what we all want when we develop a framework and release it for other people, is that one day you come and see someone's done something really weird with it that you didn't imagine was possible, and hopefully it's impactful as well. But even if it's just niche, like edge stuff, that you've given them the freedom to take it and do things that you couldn't imagine with it, I think that's the intent of like anyone who provides a driver open source. But then also the ROS team specifically, that was like, okay, this is going to be used for so many things. How do we lay the groundwork so that it's used for things that we don't even imagine it's suitable for?
That's super interesting. I think, yeah, we always need to have that in mind, like other people using our code, our robots, whatever we build. So regarding the technical challenge that you said was the biggest challenge for you at Open Robotics, I wonder how is that different from the technical challenges that you find in the medical field?
I think people's intuition that medical robotics is a lot about safety is correct, that it's like you can have the most performant feature complete robot, but if it's only safe some of the time, like you won't get ethics approval for it. And so that's a challenge that I have enjoyed stepping into, in addition to, of course, like the specific robots that I'm working on, they're really innovative robots. And so at the application level of what we're doing, whether it's skin printing or like creating 3D models from ultrasound scans of people's vasculature, that's innovative work that needs really cutting edge robotics features to be developed as well. And alongside it, we have to answer the question of like, and how do we know that it's safe? And the reason that I find that an interesting challenge is because if you were to just do safety, I guess, with unlimited resources, then yeah, you could spend, by default, I think people would think, I'm going to spend time proving that nothing in the ROS layer can go wrong. Or you'll spend the rest of your career doing that, you know, and it still won't be true. So I enjoy the strategy behind like, what can we do instead? Which is, rather than saying that there will never be failures at the motion planning layer or like comms drop out, how do we make our system robust to that? And that's actually pretty well established in other safety critical industries. And this notion of like fail safe is, okay, maybe you have something critical in whatever your device is. If it stops working, mission failure, you know? Well, that's not, you don't necessarily need it to never stop working if you can always know that it has stopped working and like shut the system down in that case. But then you keep asking these layers of questions of like, well, how then do I know that that monitoring is reliable and whatever? And it turns out to just be like an interesting problem that if you solve it well, means you save time for your innovation, in that like, if you can make your system robust and like safe worst case, like I was talking about in the ROSCON keynote, then as a result, you free up all the time that you would have spent proving to someone that your system is never going to fail. Instead, you can build new features that maybe they themselves are failing because they're experimental and whatever, but your system as a whole is robust. And like, I love that challenge. I think both of those aspects of my job, especially complementary, make for really interesting work.
And what I wonder is there a certification, or who says when it's definitely safe to use? And how do you get that criteria before starting to find those justifications of like, this is safe because?
Yeah, you know, it's interesting. So when I worked on the skin printing robot for burns patients, the robot that we bought is called the KUKA LBR Med. And this comes with a certificate that robot has been developed to medical device standards, but it's very intentionally never called a device. It's called a medical device, like a piece of equipment or something that you can tell it's a piece of a bigger device. And the reason that you can't certify a component, they say, the reason you can't certify a component is because a component by itself, you can't assess the risk of it. It is always context dependent. So if you're going to use a robot that all it has to do is imaging in our context, then the risk of collision is not the same as a robot that's doing keyhole surgery. And so that's like the clearest example of where context matters. Remind me your question.
How do you, is there like a certification entity?
Oh, yeah.
Or yeah.
So then the goal that you're going for is safe enough given the context. And even that can depend on who are you scanning. Is the person, so we're developing this ultrasound scanning robot. For some people, they might be robust to collision. For some people, it might be really important that we don't, that it's completely non-contact. And so the fact that it's so subjective to the situation means that, to answer your question of like, yes, you need a certification in the sense that you should develop under medical device standards. There are standards to comply with, but they're process standards, and the process is intentionally, what it looks like is thinking intentionally about risk, thinking intentionally about failure modes, thinking intentionally about after you release your product, there may be new bugs or threats that come in. And it's really this life cycle of how you develop your software, whether it's robotics or not, to have the caliber that safety will be upheld in a medical device. So that it's a nuanced topic, so I can tell you more about what I mean. That was a bit of a zoomed out answer.
I mean, it looks like it's kind of like objective in the certification side, but it's subjective in terms of like the context of the robot that you're mentioning. So I guess it's a kind of continuous back and forth with the organisms that certify or allow the robot to work or to be in production, right?
Yeah, what's really interesting I've found is that safe enough is so subjective that it's even like safe enough in order to get clinical ethics approval to test your treatment. Say you've developed a novel like treatment for emergency ward patients in one context or another, but they already have a standard for treating people. How do you convince someone to give your robot, your treatment, a chance in trials that is ethical to someone who's come in from the emergency department? Even that is like, it's so nuanced that it's you sometimes need to be a bit strategic, and it's like, okay, well, we won't do it on emergency room patients to start off with. We'll do it on someone who has a scheduled surgery and some sort of different population group. But yeah, that's a bit of insight into what it's like, the challenges that are not technical challenges, but that you still have to be around if you're working in medical devices.
Yeah, sounds really interesting and complicated, but a nice challenge to have, let's say. So to put everyone in context, can you tell us a bit about the imaging robot that you're working on, and where like ROS, what's the role of ROS in that robot?
Yes, at Vexev, we make an ultrasound scanning robot that automates the process of doing ultrasounds of, at the moment, dialysis patients to get scans of their vasculature that's needed in order to unblock a particular part of getting them access to dialysis. And we do that not just because our robot can make higher quality scan results, like we can make 3D models instead of just 2D ultrasound scans that are made by traditional sonographer approaches, but also because there's an immense shortage of sonographers, at least in the US. And so there are delays sometimes of months for people receiving the safe form of dialysis. So my role within that is to make the like high level scanning algorithms for how we're going to collect the patient, like how we're going to actually scan someone's vasculature. And it has similarities to SLAM problems in other contexts. So there's a lot that you can draw from in that. And as well as making sure that the architecture is set up in a way that we've like isolated the risks and made it robust to different safety concerns, and getting this like safe worst case that I mentioned in the ROSCON keynote. The role of ROS in our device in the development phase, it's the same in every robotics company. It helps you get off the ground sooner. But since we're working on an imaging robot instead of a surgical robot, I think that I'm convinced, at the moment at least, that we can leave it in our device perpetually for the continuous R&D that we intend to do for the lifetime of the device. And so what we really benefit from at the moment is all of the ROS stack that is between, like, okay, we made a URDF, we have a custom manipulator because there just weren't any off the shelf that fit. That ultrasound scanning is unique for a number of ways. So we made a custom manipulator, we provided a URDF, and then we get all of the motion planning stack up to the level where we're application level doing ultrasound scanning specific stuff again. So the sandwich of like ultrasound robot specific, generic, ultrasound robot specific, all of the generic stuff in between is what we get off the shelf from ROS, and it saves us all of this dev time that thankfully like the community has released for us to take advantage of.
So you say that ROS kind of was useful for this SLAM part of localization and moving around the arm. How do you think is like the state of art of localization navigation for medical applications?
I'll correct a little bit what you said. The ROS stuff is not necessarily, it's not that we have like off-the-shelf SLAM stuff, or not yet at least, that the ROS layer, or like using ROS specifically at that layer, because it's still an innovative application of SLAM that it's like, we don't quite get it off the shelf as is, but I think a lot of other, but what it does, why it is helpful to be part of the ROS community there is because we can see how other people are incorporating SLAM into their contexts and use that almost as, imagine that maybe you don't have to imagine, but you're a team of roboticists that are pushing cutting edge applications in whatever context, but you yourself are not like doing a PhD on anything in particular. And so you're going to have an easier time if you can access a community of people who have this ethos of like, how can we lift each other up? So that's been my experience in designing the SLAM. And I made the distinction because the state of the art in SLAM or like localization in medical robotics is not really using ROS by default, and so there is that distinction between like robotics in general algorithms and then like the ROS implementation of them. Hope that answered. Oh well, I didn't really answer you. So then the state of the art is that you'll usually embed something for your localization. Sometimes, so for ultrasound, for example, people can get like gold segments, like pieces of gold metal embedded in breasts for breast ultrasound. I've seen this in some studies at least, and so like fiducial markers are really the standard for location in any medical application. We're trying to go for like that's how SLAM started in mobile robotics as well. You'd put whatever markers around your hallway that you needed, but as time goes on, our algorithms develop to the state that we can do markerless SLAM, and so that's probably the direction that medical SLAM is going in as well. But I don't think I've seen many markerless SLAM algorithms in the medical context, because it's not worth the risk, maybe.
Yeah. Maybe it's just grabbing, as you say, what the community offers and trying to apply it to the field that you're working on, either it's medical or any other field. And I wonder, what tool of simulation did you use for this project?
Yeah, obviously the people's first reaction is like, people think RViz is a simulator, and the easiest distinction to make is like, no, like RViz is visualizing stuff. But you can get a long way with just having Okay, the visualization part isn't important, but just having forward kinematics and open loop control, you can make movements. You can have a whole open loop test suite that is different planned movements just based on the URDF behaving as it should. When simulation is needed is more when you're like interacting with an environment. And interaction is a key word because sometimes even like taking measurements, you still don't need a simulator for that, but you might need something that like emulates or mocks what data you would see if you happen to have a sensor and be in the real world. To be sure, I have, through the Ross Medical community that I set up, made touch with, or like come to discover that people have developed an ultrasound simulator in Gazebo that will take CT data as ground truth and then do like the physics simulation to make mock ultrasound images. But more interesting to me is that that's not always what is necessary for an algorithm that you're developing. If you're developing something that is collision avoidance, you don't necessarily need ultrasound images to develop that. You just need awareness of proximity. And I think, and so sometimes people jump too extreme on their like simulator needs. And the reason it's not obvious, or the reason it becomes obvious that you can do sidestep things is when you're working with ROS and you're forced to make these abstractions of like literally what is your controller consuming. The controllers that I design, they don't consume ultrasound images, they consume proximity measurements or somehow other distance measurements to a surface. And so then you literally see that that block of code does not require an ultrasound simulation to be mocked or tested. And I have that experience, I think, from when I was working at OSRF. In addition to working on ROS2, I was kind of running this industrial robot arm simulation competition for NIST that was in Gazebo. And there are some competitors could use a configuration of sensors that all cost money, and the cheapest one was just a proximity sensor, and that was literally implemented as like, or not even proximity, but just like optical presence, you know, like binary on or off, like you would have on a conveyor belt. And that was literally implemented in the simulator as like ray tracing. Okay, is there something there reported literally? But then we had this other sensor that was more expensive that could tell you what object it was looking at. And they were doing bin picking, and so to know what object you were looking at was relevant. But I was doing the back end of the, like, how this competition was implemented. Do you think that I did like point cloud interpretation of the different shapes in order to decide what object I was looking at? No, I had access to the ground truth, and there's a sensor in Gazebo that's called a logical camera, and it just knows the name of the model because it has access to that data in the simulation of like the objects that are in the simulator. And so for competitors, what they needed was to know what they were looking at. But that doesn't mean that they needed to do like point cloud object recognition. If you can mock it with this like logical camera approach, you can sidestep having like getting in the rat's nest of like a point cloud interpretation problem when what you really are interested in is just bin picking. So that applies in so many different contexts. And thinking, you can save months off your roadmap, right? If you think carefully about what you actually need to simulate. And when you're working on a medical device that people are waiting on because it will save lives, shaving months of a roadmap is work that I'm really proud of.
Yeah, I think this is really interesting because I think it applies to something that she said before about there's no need to find a certification, or like maybe we as engineers in general need to spend time thinking about the problem and all the possible solutions rather than going ahead and finding like the most complete solution. Maybe it's not needed at all. So I think that's really interesting.
But the reason that we're not always the best people to do that is because, at least for me, it takes immense discipline to not follow those rather. I want to make the point cloud like object detection algorithm. I want to do that. But that doesn't mean that it's useful. If it actually, in terms of like the impact that it would have, and I remember literally on that project when I was working on the simulation competition for NIST, that was the moment in my career that I developed a mantra for myself of like, just because it can be done doesn't mean that it should be done, because productivity is not the same as like impact and moving a product forward. So and there are some features that we work on for ourselves just because every so often it's nice to like let the dog off the leash or whatever. But it takes a lot of discipline when your top goal is, ship a product that people are waiting on.
Yeah, I think also if there are a lot of constraints, as you mentioned, related to our project. So it's not only getting the best and most complete and the solution that is most interesting to us, it's also like, what can we do with the resources that we have available to get this project in time?
Yeah.
Something that I wanted to ask you as well is, you talked at the ROSCON talk. You opened the ROSCON last year. And I wanted to ask you, like, what advice do you have for people that want to give a talk that is more technical, and how do you attract the audience?
Yeah, this is probably the other thing that roboticists are not well equipped to do, like not implementing features just because they're interesting. That's a challenge. And then the other challenge is communicating the things that we have implemented to people who didn't implement them themselves and maybe are a bit like, okay, what are you talking about? So the techniques that I intentionally use and have developed as like a science communicator is to take it to the level that people care about. And I've kind of trained this behavior of mine by watching other people's talks and paying attention to what makes me go, what am I doing here? Like, what is this person talking about? And then I go, oh, that joke didn't land, or like, I'm just so not interested in this because they haven't spent the time to set the context or build rapport or whatever it is. And so having people understand why they should care about the work that you're doing, that's like the main thing that I think technologists miss when we're communicating stuff that we just know is really important to us. And then the second thing would be that we sometimes, even if we nail that, sometimes we forget to tell people how to feel about that. So maybe I've done something that's an incredible innovation and I have managed to convince you that it's impactful and whatever, but it is useful to just take people one step further and be like, and this is exciting. Like, put into words how you'd like them to respond, which can be difficult when you're also like managing the stress of speaking in front of 1,000 of your peers. But that's what makes people come away from a talk, and it goes through someone's compression algorithm. Someone will say like, hey, what was that talk about? It has to be able to go through someone's compression algorithm, and they'll say, oh, it was relevant because of this, and I feel this way about it. The rest of the details, like, people don't have to remember, but if you can communicate those two things, then your job is done. And sometimes, I guess the third point is that you maybe have to not just do that once, but do it like 5 times in the talk of like just reiterating this, that, the other thing. It's that's what I've learned.
Yeah, I really see it, like your advice. I see it on your ROSCON talk, and by the way, I really enjoyed it, and I do advise anyone that hasn't watched that talk to go watch it because it's really interesting. She talks in depth about the Vexev robot, the imaging robot that we talked today. So yeah, I'll take some time to read the questions from everyone. So if anyone else has any other questions, feel free to add them to the Q&A.
Yes,
So,
we do have 5 questions already.
okay, do you want to read them, Clary?
Yes, of course. Well, the first question from Fabri is, there are a lot of things going on with IA, health and robotics nowadays. Some things are just hypes, but some of them will end up becoming part of our lives. What's the impact you expect from these technologies on our daily life in the future, let's say 5 or 10 years?
Yeah, health, I think, is the easiest example of AI. Even 10 years ago, like in my master's, which by now it's been 10 years, I did a subject on medical imaging analysis, and the proposition of AI was because of the scale, like that you can see things in a data set of medical images that no doctor can see. And that was true 10 years ago. So imagine how much more true it is now. The amplification of diagnostic ability, not just amplification, but like, I particularly like that example because it's augmentation of like, what are humans good at? We're not good at loading 10,000 image data sets into mind, but what are systems good at, like scale? So that I think is it's already true through like fitness tracking and everything. You get these insights at like population levels, and it's going to be true in our device that we at the moment make 3D scans so that dialysis patients can access dialysis, or like a particular surgery that they need to access dialysis. But long term, if it can be eventually ubiquitous, this robot and this imaging modality is ubiquitous enough that each of us can get a scan as often as we measure our blood pressure with a blood pressure cuff, then that data point combined with immense data sets means that we can predict when someone is developing cardiovascular disease. So that's the dream.
Well, thank you, Dana. That's really great. The next question is from Jesus. Now that ROS has reached end of life and ROS 2 has been used for a while, do you think that the new features introduced in ROS 2 have been relevant, especially in critical safety environments such as medical?
So one particular selling point of ROS 2 was that we designed it on top of DDS, and that was, now we sort of take it for granted, but intentionally that was a thought out decision of like, okay, let's not write our own sort of networking stack there. Let's leverage what people already use. The examples at the time were like on naval ships, DDS is used, but you know, DDS is also used in medical devices. So my experience has been that that selling point has turned out to be useful, that actually I don't have to today work with a DDS implementation that is like, I don't think one exists that is medically certified, but there are certainly some that are more like battle tested in medical devices, even if it's not with a particular certification. I don't have to pay for that today, but the day that I want to, because I switched to a surgical robot, I just have to switch the RMW layer. And that's not an accident. That's because we were designing for this flexibility, that it's absolutely coming. It's doing its job. And some people have the experience of like, okay, well, DDS isn't a fit for my use case. And so people are switching to RMW Zeno. That's, in some contexts, that's what's right for them. In our context, DDS is DDS that has been shown to work in medical devices before, like, works for us.
Mm-hmm. Okay, great. Thank you. Next question is from Flora. Is ROS ready to interface with sensors specifically used in medicine? Has the community been building up those integrations?
Definitely the research community has. So I have invited some people to give like lightning talks on there's a tool called Slicer. I'll be honest, I don't know exactly what it does, but it's using the medical context, and I know that there's a ROS wrapper around that. And that's going to be obviously useful in an R&D project or like in a research lab. And then it's maybe useful in deployment, depending on what the risk is around that, and also what the safety architecture is, if you can get your system robust to a particular comms failure to that driver. And I say architecture because it's like, there are choices that we can make as system architects that make our product robust to different types of failures. So if you are designing a robot that needs in its control loop to have low latency comms between a desktop and the embedded system, then that is an architectural decision of like, okay, that comms is part of the critical loop there. But there's also an architecture that sometimes applies and sometimes doesn't, where your like desktop or computer equivalent is sending requests, high-level requests to an embedded controller, and then it manages its own control loop independent of comms with the computer, and maybe it'll give some feedback or whatever, but the safety critical aspect has been kind of contained to something that then, you know, that looks very similar to a lot of industrial robotics applications that are purely real-time embedded in just the safety communication. So architectures that are robust to loss or whatever failures to talking to medical device sensors will be the ones that are first able to use ROS integration without including safety risk or like inheriting safety risk in the fact that it is ROS instead of something else. Not that the something else is by default like flawless either.
Mm-hmm. Great, thank you. Two more questions left. The next one is from Flora as well. When you left Open Robotics, did you get the chance to submit updates to ROS as part of a project you were working on? And if so, what's the one you enjoyed the most?
This is a good question. I think my contributions to the ROS community since working on the, as I'm speaking, I might change my mind, but for now, I think I haven't made code contributions to ROS, at least not the core, since working on medical devices instead, but it's more the philosophical contributions and the community contributions. So by philosophical, I mean like being a leader in how ROS can coexist in certain medical contexts. And then in a community sense of like setting up the ROS medical community so that we can all learn from each other who are sort of experience, like having the same internal debates about that compatibility, and also just learning from other experts. You know, we have safety critical experts. Jeff Biggs came and taught us about like different diagrams to read that you can use to not just reason about the safety of your robot, but communicate that reasoning to non-roboticists so that you can engage with that like dialogue and get their feedback. I think the code that is like nearly available for us to, or like we're sitting on, but only because someone else doesn't seem to need it yet. I've advertised to the community, the ROS medical community, that we have developed like an ultrasound messages package internally, and put some thought into how to make those it sounds like, oh, it's just going to be the same as an image, but even the image messages in ROS, they're very intentionally thought out so that it is abstracted away from like any specific camera, or maybe it's from simulation, and having a message type and collection of types in the context of ultrasound imaging that is transferable to different sort of beamformers and stages of beamforming process. We have it when other people are interested in that.
Okay, great. Last question here from Franco. Throughout your career, you faced several challenges among several job positions and different projects. What is the most important soft skill, or what's the recommendation you'd give to all the audience here that sees you as a role model and they'd like to become a seasoned roboticist like you?
One piece of advice. I think the thing that ethos, I can tell from interacting with other roboticists, the way that I have like lived my career that's different to other people's is the emphasis on community. So when I was the only roboticist working on a skin printing robot, the only roboticist at my company of like 90, I intentionally latched on to like the team at KUKA of like, hey, you're now I told them like you're recruited into my virtual robotics team. I built this virtual robotics team, not just so that I had somebody to, be a teammate and like I could speak robotics with, but because they've seen so many more robots than I have just by virtue of their position as system integrators for everyone else's robots and medical robots. So I learned so much from them. And that's the same thing that I'm bringing to like the ROS medical community, is like, what can I learn from people who have already encountered their own challenges and learned their own lessons from them? Please share them with me so that I don't have to. And that, I think, came from working at Open Source Robotics Foundation. Like ROS, when I was in the core of ROS 2, we were like 5 people. People would come, they'd be very, first of all, like disappointed, and second of all, concerned that there were so few people in the ROS team as the core. But ROS as an ecosystem is not the ROS core maintainers and developers, it is the community. And so to see what we accomplished as a community in the spirit of ROS is what motivates me to then intentionally reach out and sometimes form communities so that I can channel everyone else's energy into the innovations that I'm working on still today.
Sounds awesome. If you can think of any communities that we could join now, I guess you have several in mind, but maybe you can mention some of them.
Yeah. So an example is, so Camila and I have met through the Women in Robotics community. This is particularly in different stages of my career. This is important or not. When I was there in Silicon Valley on the ROS team when the Women in Robotics like community sort of got set up, and I remember going to the first picnic. It was like 5 people, and it didn't really scratch an itch for me at the time that I had, because I think there were enough women in tech events in Silicon Valley that I always felt like I could get my fix of like being around other women technologists, which is really important to me because it's like the intersection of 2 ways that I'm quite unique, and there aren't many people in that intersection. So now I work entirely remotely from Portugal. I moved to Portugal with no network at all, and to build up a network of women in robotics in person in Lisbon, like I'll be doing it for the rest of my life maybe. And I have made efforts to do that. I build women in tech communities in Lisbon. But for something as niche as like women in robotics, I leverage the Slack group that has thousands of women in robotics. And because of being in that network, I then put out a call of like, does anyone want to be in this particular group that I'm forming? And then people join it. And I have access to people when I'm trying to build a community. You still have to build it, but sometimes the hard part of building a community is accessing the people that you want to join it. And like another thing happened this month, I made a book club on systems thinking in a community that's called Tech Leading Ladies. They're based in Australia. I still go to their events from Portugal because why not? And I was like, hey, putting together a book club, who wants to come? Instantly, we have a book club of 10 people, not because the community made the book club. I made the book club, but I needed access to the network of people. Same thing with the Ross Medical community, but that you can more imagine.
Thanks everyone for joining. Thanks Deanna for your time. It was awesome to meet you and hear all about your projects, your knowledge, your advice. Thanks everyone for taking the time to join this initiative. And yeah, have a great rest of your day.